Hello chemistry students. In this video, you will learn about definition of an ideal gas. You will learn variables used to describe behavior of an ideal gas. You will learn ideal gas law, Avogadro's law, and then we will see how to find molar volume, molar mass, and density from ideal gas law. At the end, we will see initial and final condition problems using ideal gas law. Let's see the definition of an ideal gas. An ideal gas is a theoretical concept developed by scientists to learn behavior of gases. For a gas to be an ideal, there are following governing assumptions. The gas particles have negligible volume. That is the first assumption. The gas particles do not have intermolecular forces with the other gas particles. The gas particles have perfect elastic collisions with no energy loss. Since neither of those assumptions can be true, there is no such thing as an ideal gas. A real gas is a gas that does not behave according to the assumptions that we described here. However, at the conditions of temperature and pressure that are normally encountered in a laboratory, real gases tend to behave very much like ideal gases. The only time real gas do not behave like ideal gas is when a gas is either cooled to near the temperature at which it liquefies or compressed to a high density that the molecules are quite close to one another. In any other situation, the ideal gas model or law that you will see in next few slides is appropriate for describing any real gas. We can describe the behavior of ideal gas with the help of these four variables. We will see these variables in next few slides one by one. So first variable is volume of gas, and we represent this by V. Next variable is temperature of the gas, and we represent this by T. The pressure of a gas is represented by P, and number of moles of gas in our sample is represented by lowercase n. Okay, so the first variable is volume. Volume of any gas sample is equal to the volume of its container, and the symbol V is used to represent volume. The units that we normally use to represent volume is liters, the symbol is L, milliliter, symbol is ml. You need to know how to convert milliliters to liter and liters to milliliter. You also need to know that 1 liter equals 1 decimeter cube. Decimeter cube is normally used to express the volume of solid substances, whereas liter is used for the liquid volume. Similarly, 1 milliliter equals 1 cm cube or centimeter cube. Centimeter cube is used to express the volume of solid substances, and milliliter is used to express the volume of liquid substances. Now, point to remember here is whatever unit of volume is used, use it all the way throughout the problem. You may have to do some unit conversion before you use the volume in the ideal gas equation. And you will see when we will do some examples. The second variable that is used to define the behavior of gas is temperature. The temperature of a gas sample is a measure of how much energy the gas contains, which is demonstrated by how fast the molecules are traveling or how much kinetic energy the gas have. The temperature used to describe gas behavior is Kelvin, and if the Celsius or Kelvin temperature is given, you have to convert those temperature using these formulas to Kelvin. Kelvin scale is used in gas law problems because the pressure and volume of gas depend on the kinetic energy or motion of the particles. The Kelvin scale is proportional to the kinetic energy of the particles, and according to the relationship between Kelvin temperature and kinetic energy of particles, 0 Kelvin, which is normally known as absolute zero, so 0 Kelvin means zero kinetic energy. And this 0 Kelvin is the coldest temperature where a matter can be, and also where the matter has zero energy. So remember that temperature must be on the Kelvin scale for any gas law calculations, and 0 on the Kelvin scale, and the lowest possible temperature is called absolute zero. The third variable to define the behavior of gas is pressure. Pressure of a gas is created by molecules of gas hitting the wall of the container. The pressure is defined as force per unit area, and symbol P is used. We live in the atmosphere of pressurized gases. You might have seen this demonstration in this image before, where when a can is filled with air, molecules batter the outside and inside of the can equally, and as a result, this wall feels no net pressure. But if we remove the air from inside the can, then with no opposition from inside, the pressure that is exerted by outside gases can crush this can. And the way this can collapses tells us that there must be some external force that crushed it inward. And that external force is actually the billions of fast moving air molecules in the atmosphere that are colliding with the outside wall of this can. Each collision exerts an inward force on the can, and the force from these collisions is felt over the entire surface of this can, and this is referred to as atmospheric pressure. The units that we use to express pressure are the most common unit that you will see in this chapter are atmosphere. The symbol is ATM, and another unit is millimeter of mercury. Symbol is mm of Hg. There are other units like Pascal, symbol is PA, and kilopascal. Again, the key here is whatever unit you are using, you will be using that unit throughout the problem, and you may have to do some unit conversion before you put the unit in the ideal gas equation. Let's see what is atmospheric pressure. Atmospheric pressure is defined as force per unit area exerted against a surface by the weight of air above the surface. Atmospheric pressure decreases as the height of a surface above ground level increases. Our atmosphere is consist of 21% of oxygen, 78% of nitrogen, and remaining 1% is other gases. This proportion of gases, oxygen, nitrogen, and other gases remain same at the sea level as well as at the higher mountain altitudes. But it is actually the density of air which decreases as the altitude increases. So if we look at the pressure at the sea level where we have the higher or normal density of air, the pressure is 29.92 inches of mercury. But if we go at the higher altitude like in Denver, where we have the less dense air, pressure is 24.92 inches of mercury, which is the pressure decreases as the height of the surface above the ground level increases. The atmospheric pressure is measured with an instrument called barometer, and this barometer actually uses mercury as one of the component to determine the atmospheric pressure. That is why it is called mercury barometer, and the atmospheric pressure is referred as the barometric pressure. In this setup, we have mercury in a container and we have glass tube immersed in this liquid mercury. In this setup, we have air molecules inside the tube and outside the tube pushing this mercury down with the equal force. But if we remove this air from inside the tube with the help of a vacuum pump, then when we have a vacuum inside and no pressure from inside the tube, but we have a air pressure from outside the tube, due to this air pressure from outside the tube, the mercury will be pushed inside the tube and will start to increase. It will keep increasing until the height of the mercury or the weight that is exerted by this mercury level is equal to the weight that is by the atmospheric pressure outside the tube become equal. At that point, the mercury level will stop. On normal average day at the sea level, this stopping point is at 760 millimeter of mercury. This pressure is known as standard pressure and referred to as normal conditions in the atmosphere at the sea level. We can also write a conversion factor with this, that 1 atmosphere equals 760 millimeter of mercury. Standard temperature and pressure is actually a very common phrase in chemistry, and it refers to nominal conditions in atmosphere at the sea level, and it is abbreviated as STP, where standard temperature is 0 degrees Celsius or 273.15 K, and standard pressure is 760 millimeter of mercury or 1 atmosphere. The high pressure systems typically have light clouds or no clouds at all, and it indicate fair weather without any rain. In the regions of low pressure, the air rises, and as it does, the air cools and clouds form from the humidity inside the air. So, low pressure reflects the rainy or cloudy day. The fourth variable is amount of gas. Amount of gas present is actually measured in moles or in grams. In ideal gas law, we will be using moles. So if grams are given, you will be converting them into moles. And N equals 1 means 1 mole of a gas equals 6.022 times 10 to the 23 molecules of the gas, which comes from the Avogadro's law. To understand the behavior of an ideal gas, we will see three cases, and the outcome of those three cases will help us derive the ideal gas equation or the ideal gas law. So the first case that we will see is at constant temperature, what happened to the pressure exerted by a gas confined to a container when we increase or decrease the volume of the container. So let's draw two containers in order to solve this case. Okay, we have these two containers. The first container have 1 liter volume and second container is 2 liter volume. We have 9 moles of gas in this container. The volume is 1 liter, but if we increase the volume of this container from 1 to 2 liter, but remember we are not adding or changing the number of moles, so we still have the same number of moles, but the volume is increased. Now what will happen to the pressure exerted by the gas molecules to the container? Remember that gas in any container exerts pressure because the fast moving particles strike the wall of the container, exerting the force on them. So if your answer is that by increasing the volume of the container, the pressure will decrease, your answer is right. And from this case, we can derive a relationship between pressure and volume, and that relationship is that pressure is inversely proportional to volume. If we increase the volume, the pressure will decrease because you can see we have same number of moles, now we have more space, pressure will decrease. And if we decrease the volume, the pressure will increase. So the relationship between pressure and volume is inverse relationship. This mathematical relationship between volume and pressure was discovered in 1662 by English chemist Robert Boyle. The second case that we have is at constant volume, what happened to the pressure exerted by a gas confined to a container when we increase or decrease the temperature of the container. Remember that temperature is directly related to the kinetic energy of the gas. More temperature means more kinetic energy, and the molecules will be moving with a very high speed, exerting more pressure to the wall of the container. And low temperature means that the molecules' speed will be slowed down and they will exert less force on the wall of the container. So if the higher temperature causes the molecules move faster and strike the wall of the container with more force, means that the pressure of the gas increases when its temperature increases and decreases when its temperature decreases, and we can derive a relationship between pressure and temperature from this case, which is pressure is directly proportional to temperature. This relationship was first expressed mathematically by French chemist Gay-Lussac in 1802. The third case we have is what happened to the pressure exerted by a gas confined to a container when we increase or decrease the amount of the gas in a container. Now for this, let's assume that we have one container with 15 moles and we added more gas to this container, and now we have 30 moles of gas in this container. The volume is same, we are not making any change. The temperature is same, we are not making any change to the temperature as well. But the number of moles are increased. So what will happen to the pressure? Here we have 15 moles hitting the wall of the container exerting some pressure, and here we have 30 moles hitting the wall of the container exerting some pressure. So the pressure of a gas actually increases when the number of moles of gas increases and decreases when the number of moles decreases. So the relationship between pressure and mole is direct relationship. Okay, number of mole increase will increase the pressure, and if we decrease the number of mole will decrease the pressure. Ideal gas law is actually an equation that describes how pressure, volume, amount of gas, and temperature values of an ideal gas are related to one another. And that equation is called ideal gas equation or ideal gas law. The three cases that we did in previous slides, if we summarize the outcome of those three cases, we will get the ideal gas law. So let's write down those three cases. The first was the pressure is inversely proportional to volume. The second was the pressure is directly proportional to temperature. The third is pressure is directly proportional to amount of gas. When we add all these three, we will get pressure is proportional to Nt over V, inversely proportional to volume and directly proportional to N and T. Like any other mathematical equation, when we get rid of this proportional sign, we need to add a constant. And when we do this here for this ideal gas equation, we will use a constant R. This R is the ideal gas constant, and it has a constant value that you need to memorize. That value is 0.0821 liter atmosphere per Kelvin per mole. You have to memorize this value with its unit, because if you change the unit from atmosphere to millimeter of mercury, it will have a different numerical value here. Similarly, if you change the value of volume from liter to milliliter, this R will change. So when you are memorizing, memorize the value of R with its unit. The other thing is, this is the ideal gas law, but we will simplify it as PV equals nRT. All ideal gas law problems that we will do in this chapter, we are going to start from this equation. Let's do this problem. According to the ideal gas law, what would happen to the pressure of a gas if you double the amount of the gas in a container while also decreasing the volume of the container to 1/2 of its original volume? So for ideal gas, all problems that we will start from the ideal gas law equation, and we will write that equation as PV equals nRT, and then whatever rearrangement we need to do, we will do from this equation. What you have to find here is what will happen to the pressure. So the first thing you have to do is you have to rearrange this equation for pressure. Rearranging an equation for a variable means you want this variable to be just by itself at the numerator. So it is already at the numerator. Now you just want it to be by itself, means you want to get rid of this volume. So you can divide both sides of the equation by volume. This will cancel and you will have P equals nRT over volume. Now, if you look at what is given is if you double the amount of the gas. So right now, the amount of the gas here is 1. So the coefficients that we have with all these variables are 1 right now. Like this is 1p, this is 1n, this is 1t, and this is 1v, right? That's the initial conditions we have. But what would happen if you double the amount of the gas? So if you are doubling the amount of the gas, it means that it is 2n, while also decreasing the volume of the container to 1/2 of its initial volume. So if the initial volume is 1, when you decrease it to half, it will be 0.5 V. And the rest of the, so constant, no change to that, and temperature, no change to that. Now you will be simplifying these numbers, and after simplification you have 4 nRT over V. Okay, now what would happen to the pressure? You have to compare this final condition with the initial condition that we had. So initial condition was that you have nRT over V and there was 1 here, right? So this was the initial condition. Now what happened here is this side is increased by 4 times. So the pressure will also increase by 4 times. So your answer will be pressure. If, for instance, you have some numbers given and you are solving this problem and you came up with a number which is zero point 0.5 nRT over V, you will again compare this number with the number that you have in the beginning, and you can see that now this side is decreased. So if it is decreased, your answer here will be the pressure will decrease by half. Let's see another example, and for this example you guys can pause this video, solve the problem at your own, and then play the video to check your answer. So according to ideal gas law, what would happen to the pressure of a gas? Okay, so again you have to rearrange your equation for pressure. Okay, that is my step number one. I need a correct equation to solve my problem. So what would happen to the pressure of a gas if you double the amount of the gas? So amount of the gas was 1N before. If I am doubling, it means it is 2N, while also tripling the Kelvin temperature. So the Kelvin temperature was 1T before. When I triple it, it is 3T. And when I simplify this equation, I have nRT over V. Now you will compare this number with the initial conditions that we have, and you can see that this side is increased 6 times. So your pressure will increase by 6 times. Now we have another problem with some real numbers, and for this problem as well we will be using PV equals nRT. So how about you guys pause this video and solve it at your own, and then play the video to check the answer. So first of all, we will make the list of all data that is available. Okay, so we have to find N. Next, we are going to rearrange our equation for number of moles. Okay, so this will be our rearranged equation to find number of moles. Now, remember, if you are using R, you need the volume in liter, which is given in milliliters, so you have to do a unit conversion here. Pressure you need in atmosphere, and this is given in 745.5 millimeter of mercury, so you need a unit conversion here. Temperature is given in Celsius, you need to do a unit conversion here. So let's do all those conversions. Remember the conversion factor between millimeter of mercury and atmosphere. We did it in one of the previous slide when we learned about atmospheric pressure. That conversion factor is 1 atmosphere equals 760 millimeter of mercury. To have the proper number of sig figs, we will always be using this pressure as 760.0 millimeter of mercury. This 1 is the exact number, and here we will count the sig figs. We want to get rid of the millimeter of mercury, so that will be the denominator. Okay, so these are the numbers that I have on my calculator. if I have to do the rounding, so we will not do the rounding at the conversion stage because we will be using these numbers in next step, and then there will be too much rounding. So what I will do here is I will just make a bracket for the proper number of sig figs that we have. So here we have 4 sig figs, here we have 4 sig figs. So if I have to do the rounding, I will be doing rounding up to this point. Right, so I'll just make a bracket here. Next, we will be doing the conversion of this milliliter to liter. So 1 milliliter is 10 to the negative 3 liter. Again, so here you have 4 sig figs. So if you have to make your sig figs, it will be all up to here. This is our Kelvin temperature. We are doing addition. Rule for addition is look for the decimal place. So here you have 1 decimal place and 2 decimal place. If you have to do rounding, you will have up to this point. So I have my all right units that I can plug in this formula. So I'll just go ahead and have all these numbers here. I'll bring my brackets as well. Okay, and then we will do the calculation. And remember, when you have multiple numbers at top and bottom, keep those numbers in parentheses. Okay, so let's look at the units. Atmosphere is cancel, liter is cancel, Kelvin is cancel. You have mole in the denominator and in the fraction, so this mole will actually be come up at the top as a unit. So you have the right unit for the mole. That is also one of the check for you that you are doing right. Now we will be doing the rounding to the proper number of sig figs. So under this bracket we have 4 sig fig. Under this bracket we have 4 sig fig. Under this bracket we have 4 sig fig. And this one we used it first time, but this have 3 sig fig. So if we are doing rounding, we will be doing it up to 3 sig fig, and your answer will be up to 0.0100. Here we have another example, so please do this example at your own and then check the answer here. So in this example, we have an automobile tire at 22 degrees Celsius with the internal volume of 20.0 liter. It is filled with air to a total pressure of 30 psi, which is pound per square inch. And the first thing you have to find is what is the amount in moles of air in the tire. So let's just solve up to this point and then we will see what to do for the next. As usual, first we will make the list of all the data that is given. So temperature is given. So here is all the data that we have. Next, we will rearrange our equation for n. So we did it in the previous slide, but let's do it again. For this formula to use, we need our pressure in atmosphere. Volume is already given in liter, so we don't have to do anything here, but we do have to change the temperature from Celsius to Kelvin. So let's do the unit conversion. So here we will be simply adding 273.15. Okay, and again we will be just making a bracket for rounding, but will not perform the actual rounding. So here we have 0 decimal place, and here we have 2 decimal place. So if we have to round, it will be up to this point. Liter is the correct unit. We don't have to do anything here, but psi, we have to convert it to atmosphere. So conversion factor is given here. We will be using this conversion factor. 1 atmosphere is 14.696 psi, which is pounds per square inch. So this unit is cancelled. So here is the answer on my calculator. I have 3 sig figs here and 5 sig figs here. So if I have to do the rounding, it will be up to this point. So these are all my numbers. Now I can plug everything in this formula. So pressure is 2.04137. I'll bring my bracket here as well. Okay, next we are doing our calculation. So for units, atmosphere is cancelled, liter is cancelled, Kelvin is cancelled, and you have mole in your answer. For sig figs, under this bracket you have 3 sig fig, here you have 3 sig fig, under this bracket you have 3 sig fig, and here you have 3 sig figs. So you will be rounding it to 3 sig figs, and your answer will be 1.68 moles. So I will write down answer here. We have 1.68 moles. So these 1.68 are the moles of air, right? Now if you look at number 2, for number 2 it says that if the air were entirely nitrogen, how many grams of it would be in the tire? So if the air were entirely nitrogen, it means these moles that we find in the previous step are actually the moles of nitrogen. So with this information, we can easily say that this is the moles of nitrogen. Okay, so 1.68 is the mole of nitrogen. What you have to find is how many grams of it would be in the tire. So this will be like you have moles and you have to do the conversion from moles to gram. That will be with the help of molar mass. So 1 mole of nitrogen, you need molar mass of nitrogen, which is 28.02 grams. You will be doing the rounding to the proper number of sig figs. So here you have 3 sig figs, 4 sig figs, and your answer with proper rounding will be 47.1 grams of nitrogen. Next is how many pounds of it would be in the tire. So if you have the grams of nitrogen, you can convert the grams of nitrogen to the pounds of nitrogen with the help of this conversion factor. And you can see by this chapter, you will see many things that we have learned in the previous chapters. We will be just using that knowledge. So we have grams of nitrogen we will be using unrounded number, but we know this is our sig fig bracket for 3 sig figs, right? Convert it to grams. Okay, you will be doing the rounding to proper number of sig figs. So here we have 3 sig fig and here we have 4 sig figs. So your rounding will be up to 3 sig fig and your answer is going to be 0.104 pounds of nitrogen. Our next topic is Avogadro's law. According to Avogadro's law, under identical conditions of temperature and pressure, equal volumes of different gases contain equal number of particles, which is atoms or molecules. And ideal gas law also states that volume of a gas is directly proportional to the number of moles of gas when the temperature and pressure are held constant. And we can write a mathematical expression for the Avogadro's law that volume is directly proportional to number of moles. But remember that it is only when the temperature and pressure are held constant. Now, in this image that I have here, we have 1 mole of helium. We have the temperature of helium, which is the standard temperature. We have the standard pressure of helium given. With all these things, we can find the volume of helium gas. The gram is given as well, but it is not needed. So to find volume, we will rearrange our PV equals nRT equation. And when we will do that rearrangement, we need to find volume. So we are going to divide it by pressure on both sides of the equation. So your equation will come out volume equals nRT over P. Now if you plug in the values given here for helium in this equation, let's see what is the volume. Okay, so atmosphere is cancel, Canwell is cancel, mole is cancel, and the only unit left is liter, and that is the unit for the volume. When you solve this problem, you will get 22.4 liter volume, and this is the volume of 1 mole of a gas at STP. So the temperature is a standard, right? This is a standard temperature, and this is standard pressure. So when the conditions are standard for 1 mole of a gas, the volume is 22.4 liter. Now, if we move to the next gas that we have this balloon filled with oxygen gas. We have 1 mole of oxygen. Temperature is same as the temperature of helium. Pressure is same as the pressure of helium. So all these numbers are same, and the formula is nRT over P. We don't really need the mass of oxygen, right? So this information is extra for this problem. Now, when we plug in these numbers here in this formula, we will again get the volume 22.4 liter. And same if you repeat this problem for 1 mole of nitrogen, that you will get 22.4 liter. So this actually proves that under identical conditions of temperature and pressure, equal volumes of different gases contain equal number of particles. So you have 22.4 liter volume, and the number of moles for this volume for all these three different gases is 1 mole here, 1 mole here, and 1 mole here. Now the second point for Avogadro's law, that the volume of a gas is directly proportional to the number of moles of gas when temperature and pressure are held constant. So in this image that I have here, so the temperature and pressure is constant. And we have this information given that we have 3 moles of this gas, and the volume is 30 liters for these 3 moles. With this information given, we can actually find the volume of a gas where the number of moles are given and we do not know what is the volume. We can use this information and find the volume of this gas, and also we can find the number of moles of this gas where the volume is given. So let's see how we can do it. So for this one, so 2 moles are given and you have to find the liter volume. So we will use this information. So you will get 20 liters for 2 moles. Okay. And for this problem, you have a volume given and you have to find moles. Okay, so with the help of Avogadro's law information that the volume of a gas is directly proportional to the number of moles. If the volume is increasing, the number of moles will increase. If the volume is decreasing, the number of moles will decrease. We can find the moles of a gas where the volume is given, or we can find the volume of a gas where the moles are given. Our next topic is getting the most from ideal gas law. We can use ideal gas law to determine molar mass, density, and molar volume of a gas when the conditions of the gas are specified. So for molar volume, we are not going to do it again because we did it in the previous slide where we find the volume of 1 mole of a gas. We did for 1 mole of helium, oxygen, and nitrogen. So that is the way we find the molar volume from ideal gas equation. But we will see how to find molar mass and density from ideal gas equation. Now, in order to find molar mass from ideal gas equation, we will write this ideal gas equation for N. Okay, this is our equation number 1. We already know another formula for N, which is mass in grams over mm. We did this formula in one of the previous chapter. Now both of these equations are equal to n. It means that this right side of the equation is equal to each other. So we can just write down these side by side. Now we have molar mass in our equation. We will rearrange this equation to find molar mass. Means we will move this molar mass at the top and just by itself. We will be using this cross to rearrange our equation. So mm will go up here and this PV will go down and then RT will go up over there. Okay, this is our formula. It is a very important formula. Will help you solve molar mass with the help of ideal gas equation for the gases where we do not even know the identity of the gas. We only need the mass of the gas, we need the temperature, pressure, and volume, and we can determine the molar mass. So this is one way of finding molar mass. You can also find molar mass in two steps, which means that you can find N from this equation. And once you have N, you rearrange this equation for molar mass and plug in the N that you have find from here in this equation, and that way you can find molar mass in two steps. Let's do this example. You guys have the formula for molar mass, so do this example at your own and then play the video to check your answer. So first of all, I will make the list of all the data that is given. MRT over PV. Since we are using R here, it means we have to make sure that this volume is in liter and pressure is in atmosphere. For temperature, regardless you are using R or not, you have to make sure that this temperature is in Kelvin. So let's do the unit conversion. We have 4 sig figs here and 4 sig figs here. Here we are going to convert millimeter to atmosphere. Four sig figs here, 5 sig figs here. If you have to round, you will be rounding it up to 4 sig fig, which is here. You have 1 decimal place here and 2 decimal places here. So if you have to round, you will be rounding up to this place. Now let's plug in all these numbers in this formula. We have 1.56 gram. R is 0.0821 liter atmosphere per Kelvin per mole. Temperature is 295.85 K. Here is my bracket. Denominator, we have pressure as 1.652105 atmosphere. Here is my bracket, and the volume is 0.2500 liter. We will do the calculation on calculator. Answer is 91.7406208. The unit that we have left is liter is cancelled, atmosphere is cancelled, Kelvin is cancelled. Unit left is grams per mole, which is the unit for molar mass. Here, if you're doing the rounding, you have 3 sig fig here, 3 sig figs here, 4 sig figs here, 4 sig figs here, and 4 sig figs here. So if you have to do to the lowest number, this will be your answer. 91.7 grams per mole is the molar mass of this gas. Now, this one I will say is your method 1 to find molar mass. Okay. You can find molar mass in 2 steps, and if you're doing in 2 steps, let's do that here as well. So first you will find number of moles. Kelvin is cancel, atmosphere is cancel, liter is cancel, and you can get moles. You will be rounding it to 3 sig fig, which is the lowest number of sig figs from here. So these are your number of moles. Then you will use the other formula, which is N equals M over mm. And when you rearrange this for molar mass, you have M over N. Okay, so you are going to have 1.56 gram divided by 0.017004463, and your sig figs are 3 here. And these are your moles. And your answer is 91.740621 grams per mole. And if you round it to 3 sig fig, you will get 91.7 grams per mole. So your answer is same no matter which method you do, method 1 or 2. These are just 2 different ways of finding the molar mass. Okay, so now we know our molar mass for gas is 91.7 grams per mole. We will do this part B of this problem. Part B is combustion analysis reveals the empirical formula of this gas to be NO2, and what is the molecular formula? Remember that for this you have to divide molar mass of molecular formula by molar mass of empirical formula. If you want to learn this in detail, make sure you watch the video for empirical formula. You will see how we came up with this formula. So molar mass of empirical formula, here you have 1 nitrogen, so 14.01 plus 16 times 2, 46.01 is the molar mass. So we are going to write down 91.7 grams per mole divided by 46.01 grams per mole, and you have 1.99 is the ratio that we have, and we can round it to 2. And the next step is the empirical formula. You will be multiplying these subscripts by the ratio that you find from this step. So when you will do that, you will have the molecular formula N2O4. So in this topic, we will see how to find density from ideal gas equation. Density equals mass over volume. For this problem, again, we will start with our ideal gas equation, PV equals nRT. We will rearrange this equation for N. This is our equation number 1. We know another formula for N, which is mass over mm. Since both of these equations are equals to N, it means that this right side of the equation is equal to each other. So we are going to write down them equal to each other. We saw this equation in finding molar mass from ideal gas equation as well, right? But that time we solved this equation for molar mass. But this time we are going to solve it for mass over volume because that is equal to density. So mass is already here. We are going to move this volume here in the denominator. Remember, we move these variables with this cross. So pressure, this molar mass will go up equals m over v. This m over v equals to density. So this is the formula that we will use to find density. Let's solve this problem. So for this problem, you have the formula that we find in the previous slide. Try to solve this problem at your own and then check the answer here. Temperature is given, pressure is given, you have to find density. If you look at the formula for density, it is pressure times molar mass divided by RT. So pressure is there, temperature is there, R is constant, you already know. For molar mass, the name of the gas is given, and for this name, you can find molar mass of helium from periodic table. Helium is a monoatomic gas. Its molar mass from periodic table is 4.00 grams per mole. We have R here, so we have to make sure that this pressure is in atmosphere. For temperature, regardless we are using R or not, we have to make sure that we convert it to Kelvin. Okay, so we have one decimal place here based on this one decimal place, and we need 4 sig fig, so this will be our 4 sig fig up to this point. And now we can put all these values in this formula. Okay, atmosphere is cancel, mole is cancel, Kelvin is cancel, and the unit left is grams per liter, and that is the unit for density. Okay, so if we have to do the rounding here, you have 3 sig figs, 4 sig figs, 3 sig fig, and 4 sig fig. So 3 is the lowest number, so this is going to be your answer, 0.165 grams per liter. We also have to find density in grams per milliliter, so let's do this conversion here. In standard notation, your answer will be 0.000165 grams per milliliter. You can also give your answer in scientific notation, and when you do that, your answer will be 1.65 times 10 to the negative 4 grams per mil. So both answers are correct. Now let's look at the type of problem called initial condition, final condition problems. In these problems, initial set of conditions is given. So we have a gas filled in this sealed container. The pressure of this gas is 5 atmosphere and the temperature is 200 Kelvin. We do not know what is the volume of this gas, and we do not know how much is the gas. Number of moles we do not know. But what happened is we heated this cylinder, and you know that there's a relationship between temperature and the pressure. So if we increase the temperature and we are not making any change to the volume, we are increasing the temperature, the pressure will also change. Now, how much the pressure will change, that is what we are going to learn in this topic. So we have all these conditions and we increase the temperature from 200 Kelvin to 400 Kelvin. We do not know what happened to the volume in this problem, but what we know is that there is no change in the volume. Same is for the number of moles. We do not know how many moles we have at the end, but what we know is that we have not removed any gas from this container and have not added any gas. So the number of mole is also same as it was in the beginning. So number of moles are also same as the initial condition. So what we will do for this problem is we will write our ideal gas equation for R for the first set, and when we will rearrange our PV equals nRT, and we will rearrange it for R, we will get PV over NT. Now this equation we rearranged for the initial conditions. You can write it down PI, VI, NI, and TI. So this all these variables reflects the initial condition. We can write down the same equation for the final condition. Now both of these equations are equal to R. It means that this right side of the equation is also equal to each other. So what we are going to do is we are going to write down these side by side. This equation is very important. All initial and final condition problems that we will solve will start from this equation. So let's see that we are starting from this equation, and now we have this problem that we are going to solve. So for this problem, the temperatures are given, right? There is a change in temperature, and you have to find what is the final pressure. So we have information about temperature and pressure, but there isn't any information about volume, but it is constant. Initial and final volume is constant. So what we can do, if initial and final volume is constant, we can simply cancel it out from this equation. Same thing we can do is for the number of moles. There is no change in the number of moles. Initial and final moles are same, so we can cancel that as well. And after that, your simplified equation will be Pi over Ti equals Pf over Tf. And since you are finding final pressure, this Pf, you're going to rearrange this equation, means you're going to move this Tf from here to here, and the final equation that you will use to solve this problem will be this. Now, one thing that you need to remember for this, since we do not have R in this equation, right? So if R is not there, it means you are not bounded to use atmospheric pressure. If the pressure is given in millimeter of mercury, you can use that pressure right away. You don't have to convert it to atmosphere. But for temperature, remember, you will always be using a Kelvin temperature. So if Celsius is given, make sure you convert it to Kelvin. Now, if we plug in the numbers that we have in this formula, our initial pressure is 5 atmosphere, final temperature is 400 K, initial temperature is 200 K. So your final pressure is 10 atmosphere. Okay, so you have 3 sig figs here, 4 sig figs here, 4 sig figs here, and your answer is 3 sig fig. Now let's solve this problem. How about you guys do it at your own and then play the video to check the answer. So initial pressure will be Pi, initial number of moles will be Ni, initial temperature will be Ti. This temperature is then increased to 45 degrees Celsius. So this is going to be Tf. And an additional 10 moles of gas is added. So for moles of gas, remember that initial moles was 20 and 10 more moles are added. So how many moles at the end will be this plus Ni will give you the number of moles, right? So let's write down everything that we have. So NF will be 20 plus 10. So let's first convert the temperatures to Kelvin. Okay, we need to round it to 1 decimal place because this is 1 decimal place. Same here, 1 decimal place. Now we will find our formula, and for formula, remember, we will always start with Pi, Vi, Ni and Ti equals Pf Vf over Nf Tf. So this will be our starting formula for all initial and final condition problems. So here you know that pressure is given, moles are given, temperature is given, but there isn't any information about volume. So if there isn't any information about volume, then we just cancel this out because it is constant. So your rest of the equation that we have is this. You are going to rearrange this equation for PF because that is what you have to find. Okay, so PF is already there. You have to get rid of this. And remember, when you are moving variables, you move variables along this cross. So if this you have to get rid, this will go on the other side of the equation at the numerator at the top. Now we can plug in the numbers in this formula. Okay, so kelvins are cancelled, moles are cancelled, and you will get your answer in atmosphere. Okay, so you have 3 sig figs here, 3 sig fig here, 4 sig figs here under this bracket, 4 sig fig here, and 3 sig figs here. So 3 is the lowest number. If you are going to round, it will be up to this 3 sig fig, and your answer is going to be 10.7. Atmosphere is the final pressure.